Hello and welcome back to Distributions. And first, as always, I want to thank all the nice people that support this channel on Steady or PayPal. In today's part 6, we will show that the delta distribution is not a regular distribution. So usually we say it's a singular distribution. More concretely, this means there's no locally integrable function f defined on Rn with values in R or C as always, with the property that delta of phi is the same as Tf of phi. And of course, this property should hold for all test functions phi. Okay, now as a reminder, Tf of phi was defined by the integral. So we integrate fx times phi x. And we already showed in the last video that for a locally integrable function f, this always defines a distribution. On the other hand, if we put phi into the delta distribution, we get out the value of phi at 0. Now our claim here is for no f this equality is possible. Indeed, this is a standard exercise, and here I want to show you the proof of it. Let's do it with a proof by contradiction. Therefore, let's assume that we find such a function f. So it's a locally integrable function where we usually use this symbol here. And now this property here will lead to a contradiction. Okay, now in the first step, I just want to integrate the function f itself. So we already know this gives us a finite number by assumption when we integrate over a compact set. And for this, let's simply choose the unit ball. One possibility to describe this would be simply to write that the Euclidean norm of x is less or equal than 1. And in order to get a positive number out here, we also use the absolute value inside. Then we know we get out a number a, which is a finite positive number. Now to get an idea what we do here, let's sketch the region where we integrate over in the case that the dimension is 2. There we just have this circle where we integrate over the whole disk. Now what I want to do is to go closer to the point 0, to the origin, because this is the one we are interested in. Therefore we can take smaller and smaller circles here and can split up the whole region. Of course we do this with infinitely many circles where we choose 1 over k as the radius. So we start with 1 over 1, then comes 1 over 2, 1 over 3 and so on. And then our idea is that we can simply take the union of all these rings here. And then this infinite union is again the whole disk. Okay, I don't think we need to formalize this even more because the idea should be clear. The important thing we get is that here at the integral we have a countable union. And now when you know some measure theory or integration theory, you immediately know what to do because here we have a disjoint union. We can simply write the whole integral as an infinite sum over the single integrals over the rings. Of course, this whole procedure here is very natural, but it's the thing we have to put in for the integrals. In the case you want to learn more about the details here, you can simply watch my measure theory videos. Now the result we get here is an infinite sum, a series, which has a finite value. Therefore we can conclude that the sequence given by these integrals here is a sequence that converges to 0. And we know even more, if we shift the starting point here, we can make this series as small as we want. For example, we could make it smaller than 1/2. And I take 1/2 because it's a number that is smaller than 1, and this is what we need for the contradiction. Okay, and now we can just summarize the whole thing. I only did it to show you that we find an epsilon greater than 0, such that the integral over the epsilon ball is a number b which is smaller than 1/2. So the whole explanation told you if we make the epsilon ball small enough, we can make the whole integral as small as we want. Of course, this makes totally sense if you just think of some ordinary functions. However, it also holds for a locally integrable function. Now this was just a rough idea, but I don't think you will have any problems filling in the details. For example, one detail I skipped here is that in this union we will not include 0 as a point. However, since the whole integral here does not care about a single point, the whole calculation is still correct. Okay, now with this result from the first step, we are ready to finish the proof. Because we look at the delta distribution, it would be good to have test functions that are concentrated at 0. Indeed, we already know a nice one from part 2 of the video series. It was set to 0 outside of the unit ball, and inside the unit ball it was given by an exponential function. This is a nice test function, and the one-dimensional visualization would be just such a bump, where the maximum is exactly at 0. Okay, now you already know from the first part the unit ball might be not small enough, therefore we should take this epsilon ball here. Therefore I would say let's change the function phi a little bit with this epsilon. It should be 0 outside of the epsilon ball, and inside it should be the same exponential function. Therefore also inside the exponential function we have to divide by epsilon. And then you see this was just scaling the whole test function. Everything looks exactly the same, just zoom to the epsilon ball instead of the unit ball. Okay, then let's calculate with this test function. By assumption, this integral here is given by the delta distribution, which means it gives us the value of the test function at 0. It's a positive number, hence we don't change anything when we use absolute values here. It makes everything easier because we can just apply the triangle inequality for integrals. So now we have the absolute value inside the integral. This means that we can just pull out the supremum norm of the test function. However, before we do that, we should change the region where we integrate over to the epsilon ball. Because outside of the epsilon ball, everything is 0 by the test function. And maybe now you already see why we care so much about the epsilon ball. First, let's pull out the supremum norm of the test function. And then you see only this integral here remains. First, the supremum here we already know, it's the value at 0. More concretely, the same as the left hand side. And the second part here is equal to b. However, b was smaller than 1/2. Which means we have an inequality which can't be satisfied. So we have a positive number which does not get smaller when we multiply it with 1/2. And such a positive real number does not exist. And this is indeed our wanted contradiction. In conclusion, such a locally integrable function f for the delta distribution does not exist. Therefore, the delta distribution is not a regular distribution. Okay, then in the next video I will show you what we can really do with distributions and how to calculate with them. Therefore, I hope I see you there and have a nice day. Bye!